This video is going to cover Chapter 10, Intermolecular Forces. So get out that handout for Chapter 10. You can find it on Blackboard and print it out. The outline for this chapter that we're going to discuss are intermolecular forces, and the four main forces we're going to look at are dispersion forces, also known as London forces, dipole-dipole, hydrogen bonding, ion dipole. Then we're going to look at phase diagrams, intermolecular forces at work, and polarity and solubility. So recall we talked about polarity after we were drawing Lewis structures, predicting the three-dimensional shape using VSEPR theory. So we're going to be putting that to work and determining solubility. So first, let's clarify the difference between intramolecular forces and intermolecular forces. The combination of attractive and repulsive electrical forces between pairs of electrons within a molecule are intramolecular forces. So that's the bonding that we've talked about. Intramolecular. So here we have HCl. You can see these two shared electrons between the hydrogen and the chlorine. That's an intramolecular force, the actual bond itself. What we're going to be talking about in this chapter are intermolecular forces. So if you have two compounds interacting with each other. So the intermolecular force is weak compared to the intramolecular force, but it can still be quite strong. The forces that act between molecules and between molecules and ions are intermolecular forces. So these ones. So it's not an actual bond where they're sharing electrons, but they're just interacting with each other. Intermolecular forces have considerable influence on the physical properties of all substances. The strength of the IMFs, or intermolecular forces, between molecules or atoms determines the state, whether it's solid, liquid, or gas. So how strongly the molecules are interacting with each other. If they're held together really tightly, then you have a solid. They're moving a little bit, you have a liquid. Or if they can completely separate from each other, then you have a gas. Strong intermolecular forces tend to result in liquids and solids with high melting and boiling points. Weak intermolecular forces tend to result in gases with low melting and boiling points. We're going to focus on four intermolecular forces, and in order of increasing strength, they are the dispersion force, the dipole-dipole force, and the hydrogen bond and ion dipole forces. So we're going to talk about each of those separately. The first one we're going to look at, and this is present for all compounds, are the dispersion forces. So these are the interactions of nonpolar molecules. So recall in the last chapter when we were drawing Lewis structures and then using our VSEPR theory to determine the three-dimensional shape. Then we were using the electronegativity differences of the elements to figure out which direction the dipole moments are. And then we could figure out if it was polar or nonpolar. So we're going to be using that to figure out which type of intermolecular forces are present. Dispersion forces arise from instantaneous dipoles. So let's take a look at helium. Recall that helium in the nucleus has two protons and then there are two electrons around it. So let's say we have this really high-speed camera, and this is frame 1, frame 2, frame 3. So this is just, we're just taking really rapid-fire pictures. So here the electrons are kind of on either side of the nucleus. Here they're on either side of the nucleus. But then all of a sudden, this split second, both electrons are on this side. So at that exact moment where the electrons are both on the same side, then you almost have a dipole moment where you have a partial negative charge over here and then a partial positive charge over here, simply because the electrons moved over here for that little tiny fraction of a second. So that's called an instantaneous dipole. Now in the last chapter, we were looking at permanent dipoles. This is different because in the next frame, there might not be a dipole at all, but just for that split second, there's a shift in the charge, separation or distribution, and you have an instantaneous dipole. So these occur from random fluctuations in the electron distribution of a helium atom cause instantaneous dipoles to form. All right, these dispersion forces are also known as London forces. An instantaneous dipole on any one helium atom induces instantaneous dipoles on neighboring atoms. The neighboring atoms then attract one another. This attraction is called the dispersion force. So you have this one helium atom and the electrons suddenly go over here. So you have a partial negative and a partial positive. And then it sort of causes the next one, the electrons, to move over towards the positive side. And then you can see it kind of creates this chain reaction almost. So then you have an induced dipole moment in the next one. So then they're going to kind of line up minus plus like that. And so then you have this weak interaction between the helium atoms themselves, kind of holding them close together. So let's discuss the physical properties that result from dispersion forces. Here we have a look at the noble gases going from the smallest one, helium, down to radon. So you can see they're getting bigger and bigger. Z, this is our atomic number, or the number of protons in the nucleus. And this is the boiling point. So you can see the boiling point for helium is very low, and it's teeny tiny. So the boiling point is pretty low. This is Kelvin. So it's pretty low for all of these. So these are all going to be gases at room temperature, which is about 298 degrees Kelvin. But the bigger ones have higher boiling points. So if we're just looking at dispersion force, why would the bigger ones have higher boiling points? The only intermolecular force exhibited by noble gases is dispersion. As the atom gets bigger, the dispersion force increases as a result of higher polarizability. That makes the IMF stronger, and therefore it requires more energy to separate the atoms from each other, leading to higher boiling points. So what is polarizability? Is the relative ease with which the electron cloud in a molecule, ion, or atom can be distorted, inducing a temporary dipole. So bigger equals more polarizable. So if you think of them as little balloons, if you have a tiny balloon, you can't squish it very much. But if you have a big balloon, you can squish it around a lot, and then you can kind of force the electrons to all go to one side, and that'll kind of create a higher partial negative charge. So then it can induce a bigger induced dipole moment in the one next to it, so then they can kind of interact more strongly. So it depends on the polarizability, and polarizability is just related to size. So the bigger it is, the more polarizable it is. So if you need to check back at that atomic radii trend, that'll help you figure out what's more polarizable and therefore what will have a higher boiling point. These dispersion forces are the weakest intermolecular forces. So these substances are more likely to be gases at room temperature and normal pressure, as can be seen by the below room temp boiling points in this chart. Here are some different factors that affect the strength of that dispersion force. The size of atoms and molecules. Larger atoms and molecules are more polarizable, so they're kind of squishier than smaller atoms and molecules. Dispersion increases with polarizability. So if we take a look here on the x-axis, we have molar mass, which is size, and then we have the boiling point in degrees Celsius. So you can see butane, which is made up of 4 carbons, here has the lowest boiling point. And then pentane, 5 carbons, 6 carbons, surrounded by hydrogens, 7 carbons, and then 8 carbons. As it gets bigger, it's more polarizable, and therefore that dispersion force is stronger. So they're interacting with each other more strongly, and the boiling point increases. Factors affecting the strength of dispersion. So not just size, but also the shape. Increased surface area equals increased interactions between molecules, which would correspond to a higher boiling point. Linear molecules have higher dispersion than branched molecules of similar molecular weight. So here you can look at this one as kind of linear. This has 5 carbons and it's kind of as long as it can get, and it has a boiling point of 309 Kelvin. Then if you branch it, so you take one of these carbons and attach it inside instead of in a big line, then the surface area gets smaller and the boiling point decreases a little bit. Then if you completely branch it, so you've decreased the surface area as much as you can, then the boiling point goes down even more, even though the size is about the same. So if you're ranking dispersion forces, you should look not only at size, but also the shape, the surface area. So now I want you to take a minute to practice on your own and make sure that these concepts are making sense. Rank the following atoms in order of increasing polarizability. And then rank the following molecules in order of increasing boiling point. So pause the video here, take a second, and answer these questions. All right, so polarizability, remember, increases with size. So you're going to just look at these on the periodic table and see which one is smallest to biggest. So in this case, hydrogen is the smallest, then neon, argon, krypton. So this is ranked increasing polarizability. Now this is sort of the same question. So in this first one, if you were going to rank these increasing boiling point, it would be the same series. So for these, rank the following increasing boiling point. So it's going to be just from smallest to biggest, because the only intermolecular force present is the dispersion force. So first fluorine, then bromine, then iodine. And remember, these are all part of our diatomic elements. So F2, Br2, I2. So increasing boiling point is just from smallest to biggest when you're dealing with the same type of intermolecular force. Dispersion forces are present in all molecules. Dispersion forces are the only intermolecular forces present in non-polar molecules. Dispersion forces, in addition to other intermolecular forces, are present in polar molecules. And the strongest type of intermolecular force present will be the one that determines physical properties, like boiling points, for small molecules. For larger molecules, you must consider the intermolecular forces throughout the molecule. So if a molecule is quite big, you might have different sections that have different types of intermolecular forces. Now we're going to take a look at interactions of polar molecules. So all the rest of them will be polar, but we have kind of different degrees of polarity. So we have a dipole-dipole moment when we just have a polar molecule interacting with a polar molecule. Hydrogen bonding. Even though it says the word bonding, it's not an actual bond with shared electrons, but it is a stronger dipole-dipole. So hydrogen bonding is kind of like dipole-dipole on steroids. And as the name indicates, some hydrogen is involved. Then we have ion dipole, which is just what it sounds like. You have an ion interacting with a compound that has a permanent dipole moment. So in this case, you can see a sodium cation interacting with water molecules. Now we're going to go through each three of these more closely.